So I'd like to thank the organizer for a really interesting event, and thank you for inviting me. And I'd like to apologize to the audience because I feel a little bit uncomfortable because I'm going to bring data. So my talk is really around data. And we'll see how it works.
On the left.
Oh, it's Hebrew. First of all, everything that I'm going to say, my students are part of it, and in different experiments that I'm going to mention, some of my students will be there, and I'll try to mention their names. But anyway, everything in the lab is because of the students. So these are my students. Some of them already graduated, so 2 of them are already PhDs, but...
Microphone.
Oh, microphone. Okay. Can you hear me? So I'll say a few words about the lab, and then I'll talk about the virtual reality and what we do there. So the lab basically puts together 3 components. One is we take virtual or augmented reality. We put people inside those augmented reality. It's an environment that is surrounding. It's not just, you don't need the Oculus glasses that will separate your body from the environment and your eyes from the environment, but you see your body. We can also use the Oculus, but I prefer using the kind of environment in which you look and you see the environment, but you see also virtual objects in the environment. So for instance, I can see you, and in addition to that, I can see my daughter who is right now in London. So, and she's sitting right in front of me. I bring examples as we go along. So the virtual reality is similar to this one, for instance, on the left, which is similar to what was once known as the cave. You do wear glasses, but those are see-through glasses, so that they create the illusion of 3 dimensions, just the way we get the illusion of 3 dimensions in reality. We do also functional MRI, to see the brain correlates of different events. We do EEG in order to find the neural correlates of action and different types of perceptual events, and we correlate between them in order to identify the systems that are activated, the mechanisms that are activated when particular events happen in the virtual reality. So, and then we model, we try to relate your optimal performance in virtual reality, the brain correlates, and the sensory stimuli, in order to try and find out what needs to be stimulated in order to bring you to a situation of optimal performance. Our funding comes mainly from the EU. Presentia, immersive beaming, university, some of the projects that we have. And in addition to that, Minister of Education Israel, from NIH, NSF, ISF, Microsoft, and so on. So what am I going to talk about? I'm going to talk a little bit about virtual reality, augmented reality, mixed reality. All those words overlap to an extent. It will be a brief introduction, mainly visual, so that if anybody here doesn't have a good experience or a long experience with virtual reality, at least you'll be able to see nice photos. I'll bring 4 examples around enhancement, and the 4 examples will be around perception, memory, and learning. So what are the 4 examples? So the first one is asking the question, why do we need virtual reality? Is it in any sense better than a flat video, a flat screen? And we ran a study that was the PhD of Alex Dan, who came from the Air Force and was interested in how people learn in virtual reality and simulators. And this is what we did. Is virtual reality, does it have any benefits for the way we process information compared to flat screens? So that's the first one. The second is about memory consolidation. And I will show how virtual reality could be used in order to activate those particular mechanisms that we know that are correlated to consolidation of memory. The third one is the shape of misconcepts. So I don't know if you know, but most people, something like 60-70% of people have misconceptions about how objects behave in the world. We call it physics. And now what happens if I show you a reality that behaves according to your own misconceptions? How does your brain respond to that? Does it recognize as familiar? Does it recognize it as alien? I'll bring results of that. This is work done by Lulu Guerra. She just finished a few days ago. And the last one is about errors that you make. It turns out that when you make an error, I can identify a particular signal, EEG signal, that predicts the error. If it predicts the error, can I use the virtual environment and robotic systems in order to prevent you from doing the error? Think how important this is, how crucial this is in a system in which we use virtual reality, for instance, for telesurgery. So these are the four examples, and then I will try to summarize, and I will try to raise the question of whether we can enhance, and if so, why enhance a human in virtual reality. Or not only in virtual reality, maybe if we enhance a person in performance in virtual reality, maybe we can enhance the performance outside virtual reality. This is the work done by one of my students, Rotten Bennett, and we have really exciting results meanwhile. So virtual reality is not new. Who is familiar with this kind of glasses that people, I saw it in San Jose in the museum. You put it on, you have two photos or two kind of postcards, and you put one on your right side and the other one on your left side, and you have this kind of lenses, and you look through it and you see 3 dimensions. Because, okay, I'm glad there are people who saw that, because what it really does, it creates exactly the same conditions that in which you perceive 3 dimensions in reality. A different kind of image that falls on each retina, and the difference between the two is interpreted as depth, as a 3-dimensional volume. So this was Pygmalion. It was used to make money. The other one was called Sensorama, and it was actually used. It was developed by the military. And it was in order to take radar systems and make them into 3-dimensional visualizations. So right afterwards, it was used in order for entertainment. You all know the Oculus, but the reason that I show this is because of this. I found it on Kickstarter. And what it is, it has hot air that you feel on your face, mist, water that you also feel, odors, good or bad, and so on. So it's going there. Immersions. That's a big question. What is needed in order for you to feel really immersed in a virtual reality? I mean, to feel that you are in a virtual reality and not to know that you are in a virtual reality. To believe that you are in a physical reality. So it turns out that it is not only to copy exactly reality. Actually, you don't have to copy exactly reality. And I'm going to go again to Mel Slater. Mel Slater was a colleague on several of the projects that I mentioned. And in one of the projects that was actually Presentia, in one of the projects, we had to convince the reviewer that was sent by Brussels that to really do good work and that it has any value at all, even though the visuals were not really good. So this is the cave, And this is a pub. And we took the reviewer and put him into the cave in that very bad-looking pub. And we connected the person to heart rate, and we looked at the changes at the heartbeat, and we looked at the heart rate variation. And you see this woman, she doesn't look real, of course. Now she comes closer. It was Darwin Caldwell who was our reviewer. And she comes closer to the reviewer, and she tells him, "You're new here, right? This is your first time." And he says, "Yes." And she tells him, "You know, you look good." And you could see right away changes in the physiology. And right afterwards, she waits for a few seconds, and then she said, "You know, I live just around the corner. Would you like to have a cup of coffee?" Further up. Now, it's not as if he didn't know that she's not real. Of course he knew. But there are automated systems, part of the autonomous system, that will respond automatically. And you cannot, you have to be a yogi or something else, I don't know exactly what, in order to be able to suppress that. And then we put fire in the same path. And exactly when we had fire, then we saw Darwin stepping backwards. Of course, he knew it's not real fire. And we did additional experiments with this, and there are many papers on this. It's not as if you don't know that this is not real. You do know it's real, but it affects the autonomous system in a way that makes you respond automatically, and you cannot suppress it. So I took this is from Skip Rizzo. I took this slide from him because I liked it a lot. So virtual reality is really in the head, but so is reality. And from this point of view, I agree with the previous speakers. I don't know if there is a big difference between the two. There is a difference. I don't know exactly how to point at it and what is the meaning of that. So a few other examples of virtual reality. So you see here you see on the cave, and over there you see an image of you with this kind of animal, and here you are inside. This is augmented reality. You are inside this kind of structure. And again, in other examples, simulator on this side, a molecule on the other side, and so on. And augmented when everything is overlaid. You saw examples, so I'm not going to waste time. This one I find especially interesting because you see the person at the same time. You see also a virtual image that can be used in order to study, to explore, to teach, to learn. So a really interesting application is telesurgery. I worked on the first system that was sent to a company called Intuitive Surgery, and they created the Da Vinci. Who is familiar with the Da Vinci? Thank you. So Rambam, several hospitals in Israel already have the Da Vinci. The Da Vinci is a system that would allow a surgeon to do surgery from distance. But you'll be surprised, the distance is only a few meters away. And what happens there is that the surgeon does the surgery using handles. The handles are part of a robotic arm, and the robotic arm exerts forces on the hand as if the person touches the real tissue. If you touch a bone, you feel a different force exerted on the hand, force feedback on the hand. If you touch, then touching a tissue or touching fat or touching blood vessels. So the feel is very real. It's really amazing. At the same time, the robotic arms will follow the hands of the surgeons at distance. So why, if it's only a few meters, only one room away, why is it that they use telesurgery? Because it is the robotic arm is more precise. And how does the surgeon know how to do the surgery? He has a virtual reality, of course, of the patient. And the virtual reality is multisensory. Visuals, And also you feel the force feedback, you feel the touch, as if you use a real tool. So in this sense, virtual reality would be really important to show every single detail. So here it is important to replicate reality, not so when you try to convince people to have a particular kind of experience. So what am I going to claim? Now that you know what virtual reality is, I'm going to claim that if we know what mechanisms are involved in specific cognitive functions, and we know how to stimulate these mechanisms, then we can implant sensory stimuli into a virtual world that will activate the relevant brain areas to enhance performance. And I'm going to try and convince you that this is doable in the next 10 minutes. How much do I have?
Over 10 minutes.
Okay, great. That's good. So one example that I want to take is social virtual reality and the role of a system that was mentioned before. And thank you for mentioning that. That's the mirror neuron system. So, only about, research that I didn't do. Nalini Ambadi did at Stanford, a lot of research on that. And she claims that less than 10% is actually conveyed through words when two people talk to each other, when two people converse. And everything else goes through other kinds of perceptual systems, through other kinds of visuals, other kinds of cues. So, but we don't know exactly what they are. So when we create a plastic kind of replica, which we call avatar, which is an artificial avatar, all this doesn't go through. So you have to rely on words. And of course we try to create the facial expressions, but the question is, a very good question is whether these facial expressions are realistic or not, and whether we know how to judge whether they are realistic. So what we do, we got the conclusion that it is much better to try and replicate the human instead of creating a real avatar. An artificial avatar, artificial entity, which is an avatar. So this is Bracha. Bracha is at home. Here she is. Can you hear me? Yes. So, and she was not able at that time. Her baby was in physics. She did a master's with me. She was not able to come to the lab at that time. So we created a three-dimensional image of Bracha. It's doable. Many people do that. We developed algorithms to clean up the image so that it doesn't have noise, it doesn't have all kinds of black patches, it doesn't have a hollow around her, and so on. And we got a very good image. And this is Bracha. We send it over the web, over the internet, and we project it in the lab on a huge screen from backwards. And she comes forward, she comes out of the screen to Amit. This is Amit. Amit has this kind of see-through, that you can see through the whole world. In addition to that, he's able to see Bracha coming out of the screen in 3 dimensions, in between him and the background. We implanted Bracha with a heart, and the heart pumps with the real heart rate, Brachas. And the reason we wanted to do that is because we had results and we read several papers that show that two people that work together, the HRV has the same tendency. And it makes sense, because if two people work together and both of them, they work well and both of them are excited about their work, then there is a change in the HRV, and you can see that. It's called rapport. So we wanted to study that, and that's the reason we put in the heart. So why is it important to see Bracha this way? It is important to see Bracha this way because the mirror neuron is involved in reading emotions. Because when you look at my face and I'm sad, then you see my muscles in a particular kind of state. And what's happening is that you mirror those muscles as if your muscles are in the same state, and this is how you know what is my emotional state. This is how we have empathy. This is how we mimic. This is how we learn to play piano just from looking at somebody else. This is how people first start learning how to do surgery, from just looking at somebody else. Not only this, I mean, they have to actually do that, of course. So the social interaction must involve a human-looking avatar. And the major point is that the mirror neuron system is activated much stronger when the motion is biological. So it is human motion. If it is not human motion, non-biological, it is not activated as high as when the motion is biological. So for real interaction, we really need the motion, the pattern of motion of the muscles to be biological, the way humans move. And it's not as if we know how to replicate that today. I mean, people are working with the mathematics, modeling the human motion from many, many years, and I don't know that they achieved that, at least to the extent that I know they did not. So we still don't know how to do that. So the mirror neuron system is important. That's why it is important to create the kind of avatars that obey us. So I want one more example, and this is about my outer body. So if you look at this is me, but this is the outer me. So try to imagine the following. Try to imagine together with me. You enter my lab, and when you enter my lab, it's a big room, about half of this room. And you walk, you see somebody emerging from the screen across the room, walking towards you. And you get closer, and you see that somebody looks exactly like you. Glasses. You move your head, that somebody moves the head. You move your shoulder, that somebody moves your shoulder. Not as in a mirror, but as another person that is exactly you. Now, you remember the rubber hand illusion. What I'm going to do is try to apply that to the whole body. So you see somebody touch that other you. At the same time, I make sure that you will be touched in the same point. At the same time, exactly. It must be synchronous. You develop the illusion that you look at yourself from outside. This was mentioned just before by Daniel. And why does it happen? Because, and I try to explain it really, I apologize for the simplicity. So when you touch something, the point where you see the touch, this is where you feel the touch. So there is collocation in space between visuals and between touch. So that means you integrate the two. Now I dislocated between the visual and the touch. But the brain doesn't know that dislocation is at all possible. Since visual normally, except very few cases, overrides touch, then where you see the touch, that's where you think, you feel the touch, which means you are there. We applied that to several projects. One of them was changing memories. We spilled coffee on a person. And we interviewed the person several times, a week afterwards, a month afterwards, several months afterwards. And we asked them to describe, and they described it as if the coffee was spilled on them, not on the double. I call this the double. There are people that want to do trauma, change memories that are related to PTSD, to trauma memories, and so on. But this could be also entertainment, or it could be tourism. Think of somebody who is in a wheelchair and suddenly could go to Georgia and climb the mountains. go to China, to Sanju, and see the beauty there, and walk in the woods. So this is a way to enhance the immersiveness. So I'm going now to the examples, and I'll finish soon.
You've got 5 more minutes, you're fine.
I'll have only 2 examples. So why VR? What is it better than just Skype? Why should I talk to you through a meeting room on VR and not just on Skype? Is it really better? So we did a study with EG in which we put Adva, we asked Adva to teach people how to do origami. And we had origami, she taught origami in a virtual reality 3-dimensional teacher on a 2-dimensional screen with an easy and a difficult kind of origami. And I'll show you the results. And if you look at the results, this is we measured mental load. We measured mental load with EEG. If somebody is interested in the exact algorithm of how we measure that, I can send you the paper. The paper is published. This is Alex Dunn, by the way. This is his PhD. So what we did there is that we measured the mental load with EEG in 2 dimensions with a flat screen and with 3 dimensions virtual reality. And if you look here, then the average, in this case for 3D, is about 0.8 units. If you look here, then the average is about 0.1. So 0.8 versus 0.1, that's the difference. The mental load in 2 dimensions is much higher, significantly higher than in 3 dimensions. And why is that? There is a whole theory about it. When we had to guess ahead of time what would be the result, we thought that it will be in 2D because you have less sensory stimuli to process. But then we thought the ambiguity in 2D is much larger because in 2D you don't have the depth, so you have different kinds of interpretations. But it turns out that the ambiguity adds much more mental load than processing the depths. Performance was better for those who learned in 3D. This is performance in 3D, and you see variability is smaller compared to 2D. What does it mean? The actual virtual reality actually enhances your performance, your perception and performance compared to Skype or video or whatever, which is 2D. Example 2 is expedited memory. Now imagine that the environment can talk to you. Imagine that the environment can give you some sort of a feedback to something you need to do. So suppose you need to do the following things. Don't read, try to ignore this. Suppose you're connected to EEG. While being connected to EEG, I ask you to raise a particular oscillation, particular band, frequency, it's called theta. And I ask you to do that. You have no idea how to do that. But now I'll tell you, you see these people in the virtual reality? You see those people over there? Whenever you raise that particular band, the theta, these people will walk faster. So make them walk faster. And it takes about 3 minutes to learn how to do that. There are people who don't know how to do neurofeedback, for some reason they can't do that. But those people that can do that takes only 3 minutes, including people, my mother, who is much older, of course. So now what's behind it? It turns out that I'm going now back to memory in order to close the loop. It turns out that if you learn something in the morning, you learn piano, a particular piece of Chopin, you learn in the morning and then and then you are tested right afterwards, tested in the evening, and tested the day after. It turns out the day after you're much better. And the reason is that during the night something happens that creates consolidation of memory. Turns out that during this process there is a resonance between two areas in the brain. The first one is the place where you have the first registration, which is the hippocampus, and the other one is the striatum. There are other areas too, but the other one is striatum. And then when both resonate, this is when memories are conveyed or transferred to the striatum, and you have more space in the hippocampus. And this is done with this particular band called theta. So that's why I asked, can we do it during the day? If I manage to teach you how to raise your theta, can I do it during the day? So that's why we ask people to raise theta, and we use the virtual environment, the response from the virtual environment, those people walking faster, in order to teach people, to train people to raise the theta, and these are the results. So in the beginning, we tested 4 times. Before they learned a particular task, motor task, they were all the same. Afterwards, about the same. We had 3 groups. One experimental, it's called theta. The other 2 are controls. One, we call it beta, and they raised a different band totally. And another one is control. They saw movies instead of doing neurofeedback. And now, after neurofeedback, you can see the difference. It's obvious there is a difference between the blue and the other 2, and there is no difference between the beta and the control. Look at what's happening after a night sleep. And then further and further, which means there is interaction between the process during the night and between what happened during the day. I'm going to finish here now, and I will not show example 3, but maybe I'll just say 1 sentence. And in this example, we show people who have misconceptions in physics. We have the pendulum behaving according to their misconceptions. And now when the pendulum behaves according to these misconceptions, we wanted to see whether the people that did not have the misconception identify the wrong motion by predicting that they have to, when they catch it, by going to the right place. And the people who have the misconception, whether they go to the misconcept place to catch the falling pendulum. What we found is that everybody caught the pendulum correctly, which means that even though they had misconceptions where they had to predict the motion, they predicted correctly. The results of response time show the same. The results of EEG, we looked at something which is called P300, which is an indication of seeing something which is unexpected, show exactly the same, which shows that somehow the brain knew how to identify the misconcept, although when we say it in words, when we are asked what is it that we believe in, we say the wrong things. I'm going to be done now.